There are more ways to design a computer, as there are different types of computers on the marketplace today.
I struggled with the best way to present the following video, because now we're moving away from basic logic circuits and latches and towards computer architecture. An architecture is all about the compromises one makes when balancing the needs for processing speed, power consumption, the number of transistors you can use, and the marketing needs of your computer, and the way one solves for these problems. For example, when discussing computer registers, locations where a computer can store the intermediate results of various math operations, just picking the number of registers you'll use and how you'll use them can be a complicated question. More registers means more places the computer can stash intermediate results, and that can make a computer more powerful. But the more registers you have, the more instructions your computer needs, because you need a way to tell the computer add register A into register B. And if you have 16 of each register, and you allow any combination of two registers in a math operation, you immediately need 256 separate instructions, one for each possible combination of 16 registers by 16 registers. Worse, you need far more transistors in order to handle all the registers and the circuits necessary to get the value in those registers to the Arithmetic Logic Unit, or ALU. But rather than get bogged down in all of these details, some of which involve concepts we haven't encountered yet, I've chosen to simply present our processor without discussing the compromises and requirements that may drive the design of our computer. That way, we can focus on how our computer works, rather than get bogged down in the myriad of details involving ideas that haven't even been introduced yet.
For our computer, let's start with the Arithmetic Logic Unit. For our second video, we had constructed the parts of our Arithmetic Logic Unit by building the parts for addition, subtraction, binary logic, and shift operations. Now we need a way to pick one of these operations at a time. While we're at it, we'll add this element to copy the contents of the B input of the Arithmetic Logic Unit to the output. Why we'll need this will become clear later. Now we can build a simple circuit to select which component we want to select. First, we add an AND gate, which returns 1 if the adder or subtractor returns 1 and the control line is 1. And we'll add an OR gate, which combines the signals. So if we select the adder by setting the adder control line to 1, then the output of our circuit is the results of the adder. And if we select the subtractor by setting the subtractor control line to true, then the output of our circuit is the result of the subtraction. If we repeat this for all the outputs of our circuits, then we can select which of our components to output. So, if our adder and subtractor have different values, if we select the adder component, we see the results of the addition. And if we select the subtractor component, we see the results of the subtraction. If we encapsulate our AND gates as an enable circuit and our OR gates into an OR circuit component, and we repeat this for all of the other components, we now have most of what we need for our Arithmetic Logic Unit. Depending upon which enable gate we select, we get the results for the component we want. Of course, some of our components have a carry output, such as addition or shift. We handle this by tying together these carry outputs the same way, with separate AND gates tied to the appropriate control lines, united with an OR gate. Sometimes we may want to add in the carry input to our system. Sometimes we may not. We handle this with our carry enable line. Finally, it is useful to know if the result of our math operation is 0. That is handled by using this NAND gate. It will return true if all of the output lines are 0. And it is useful to know if the most significant bit is true. While we haven't gotten to this yet, for signed math operations, numbers are negative if the top bit is 1. That is our full arithmetic logic unit. We have 10 separate operator select input lines, an input line for carry and carry enable, and status outputs indicating if the results carried, is negative, or is 0. Now that we have our basic arithmetic logic unit, we can create a number of registers to store the intermediate results of our math operations. As I noted earlier, there are a number of ways we can arrange our registers, the way we store intermediate results of our calculations. This just happens to be one way to organize the computer. First, we're going to add an accumulator register and a flag register. An accumulator register is a register which accumulates the results of math operations that take place in a computer. It both provides one of our two inputs to our arithmetic logic unit, and it stores the results of all math operations. We also use a flag register. It is used to store the results of the status bits from our arithmetic logic unit. Note that we only have 3 status bits, but each of our registers have 8 bits. The other 5 bits in our flag register will therefore be set to 0. In addition to our accumulator and flag registers, we need a way to load results into the other input of our accumulator. So we'll use what we call a bus. This is a collection of wires that carries information around in a computer. We'll add some circuits which allow the accumulator and flag registers to be written to that bus. This allows us to copy results out of these registers if we need to. Our arithmetic logic unit can also read from this bus. And we'll add 4 more 8-bit registers, registers B through E. These can both read from our bus and write to our bus. This is the basic architecture we will build to: 6 registers A through F, with an accumulator, a flag register, and 4 general purpose registers, which can store the intermediate value of various math operations. Now I know we've glossed over a number of problems. Specifically, we have 3 separate problems we need to solve here. First, what the heck is this bus thing anyway? Sure, it's easy to talk about a collection of wires carrying information around in a computer, but how does that actually work? Specifically, how do we select one register to write to our bus? Second, how do we read from the bus, or time the reading from any part of our computer? Remember that transistors, as fast as they are, still take microseconds or nanoseconds to respond. So how do we time the signals so that we guarantee a value is on our data bus before we read it in? Third, notice that we have an accumulator and a flag register writing their contents to the arithmetic logic unit and reading the results in at the same time. How do we actually make this work? In our computer, we have 6 different registers we can copy into our arithmetic logic unit or into any one of our other registers. We can solve the problem of getting the value of one of our components the same way we solve the problem of picking one of our components in our arithmetic logic unit, by using a series of AND and OR gates. But this creates a problem further down the road. At some point when we're finished designing our computer, we're going to want to connect stuff to it. But we don't know what we'll want to connect. Certainly we want to attach memory, but we may want to attach other things to it as well. So we can't use the AND OR trick like we did in the arithmetic logic unit, because we don't know how many things we're going to ultimately connect to our computer. Instead, we want to use a different approach. Suppose we have a single wire representing part of our bus. Remember that our transistors act as switches. If the top transistor is turned on, our wire's voltage turns on. And if we turn the bottom transistor on, our wire's voltage goes to 0. But more importantly, if both transistors are off, then our circuit is effectively disconnected from our wire. We can use this fact to build ourselves a new circuit by attaching our transistors to some logic circuits to make sure only one of the 2 transistors are turned on. This circuit is called a tri-state gate or 3-state gate because it has 3 separate states. When the right enable line is turned on and the data line is off, then the attached bus wire is set to 0 volts. When the write enable line is turned on and the data line is turned on, then the attached bus wire is turned on. But when the write enable line is turned off, our circuit is effectively disconnected from our bus wire. We use the symbol Z in the table to mean high impedance, or rather, that our circuit is effectively disconnected from the output wire. This circuit becomes very useful when talking about a computer bus, and as always, we can encapsulate this three-state gate into its own symbol. What makes our three-state gate so useful is that if we connect several three-state gates to a single wire, we can control which data inputs are actually written to that wire. In this example, the top and bottom gate's data inputs are off. The middle one is on. As we iterate one at a time through our gates, each gate changes the state of our common bus wire to match the state of the data wire on the tri-state gate selected. This effectively allows us to write one set of data at a time to a common wire. Now I've taken the liberty to wire up the previous example on a breadboard using NPN transistors. This white wire represents the common wire of our bus. It connects all the way from the top to the bottom. And each row of transistors is our three-state gate. These are the transistors which drive the bus wire high or low. And these transistors represent the rest of the logic in our logic gates, the two ANDs and NOT circuits of our previous diagram. These LEDs show the input data line states, and these LEDs show which circuit is enabled. This LED in the bottom right shows the state of our bus. As we enable each gate in order, notice the LED at the bottom right changes state to match the input data line. But what happens if all of the gates are turned off? The red wire that I'm touching now is also connected to our bus, and notice that when all of our output gates are disabled, none of them are driving the bus wire either high or low. The bus wire is said to be floating, which means it's subject to all sorts of interference, such as the radio signals passing through my body. As I touch the bus wire, the signal LED at the bottom flickers slightly. This is why we have two transistors, one to drive the bus wire high and the other to drive the bus wire low. When a gate is enabled, touching the bare bus wire does nothing, but when the three-state gate is turned off, the bus wire floats. Now that we know how to write to our bus, let's talk about reading the results into a register. Recall from a prior video that transistors don't switch instantly, but in fact have a short delay before a circuit transitions from 0 to 1 or vice versa. This implies that for all our circuits we have a setup time where we need to wait for our signal to stabilize before we send a signal to our register to read a value in, and a hold time where we need to wait until after the signal is sent before our results are successfully stored. What this implies is that when we turn on the write signal to our tri-state gate to write the results to our bus, or when we select a desired component in our arithmetic logic unit, there will be a short delay before our results show up. This delay is called the propagation delay. It is associated with how long it takes for our answer to propagate to the output. And as we saw from our prior video, we have a period of time, the hold delay, for which we need to wait before we can trigger our register to read. This implies that the results will be successfully stored in our register only if we trigger the clock a short time afterwards. This delay is required for our circuits to work properly, and there are multiple ways we can achieve this delay. One way we can achieve this delay is through the use of a two-phase clock. Recall from our last video the toggle gate or T-gate. Our toggle gate or T-gate will toggle its state when the input signal goes from low to high. It effectively halves the frequency of the input clock. We can change our toggle gate to change its state when the input signal goes from high to low by adding a NOT gate to the input clock. Now if we allow our clock to run on our two gates, notice what we get. The two-phase clock we want to control our system. We can use the first output signal to control when our system writes a value to its internal bus or when we should write a particular result from the arithmetic logic unit. And we use the second output signal to trigger our registers to read. We can use these clock signals to control the timing of our circuitry. Suppose, for example, we're copying the contents of our B register to our C register. If we connect the signals enabling our B register to write to our bus through an AND gate with the first clock, then the signal asking our C register to read to the second, then when our controller sends the signals to copy the contents of our registers, the clock first triggers the B register to write its contents on the bus, and the second clock triggers the C register to read the results. Now, the last problem we need to solve is for our accumulators. For our other registers, we use the register circuit we designed in a prior video. When the clock signal transitions from low to high, the value of the input lines are stored in our register and put out the output lines. This is great for our general purpose registers, but for our accumulator it creates a problem. Our accumulator is expected to provide the value to the arithmetic logic unit and save the results at the same time. Suppose we want to shift the contents of our accumulator. The output of our arithmetic logic unit shows a bit shifted upward by 1 bit position from the output of our register. But now watch what happens when we read the contents. Because we're reading and writing at the same time, things can get a little confusing. The operation may work, or the operation may fail, giving us the wrong results. Reading and writing our results at the same time can be extremely problematic. So let's consider how our register works. Each register consists of 8 edge-triggered data flip-flops, and each edge-triggered data flip-flop is composed of 2 D flip-flops. To review, each of our flip-flops changes state when the enable line to the flip-flop goes high. So when the input signal goes low, the first flip-flop is enabled, and the contents of our data line is set into the flip-flop. And when the clock goes high, the first flip-flop enable line is disabled, while the second is enabled, allowing the contents to be copied to the second flip-flop. Now, if we add a third flip-flop to our circuit, we can keep the results from propagating to the output until the clock signal goes low again. When the clock signal is high, the first flip-flop is not enabled, so any change to the data line does not change the output state of the first flip-flop. When the clock signal goes low, the first flip-flop is enabled, and its state changes as the data line changes. But the second flip-flop is not enabled, which means it does not change as the first flip-flop changes. The clock signal goes high, and the contents of the first flip-flop is then allowed to be copied into the second. However, because the first flip-flop is no longer enabled, changes to the data line do not alter the contents of the second flip-flop. The clock signal then transitions from high to low, and that allows the contents of the second flip-flop to finally be stored in the third, which is now output by our new register gate. The data line does not affect the state because at this point the second gate is no longer enabled, so it no longer changes state as the data line changes state. This creates a new gate whose contents of the input line is stored when the clock signal rises, but the contents are not written to the output until the clock line drops again. We can encapsulate this collection of gates into a new 1-bit accumulator circuit, and this is our complete accumulator, capable of reading and writing a result all at the same time. And this gives us the components necessary to create a simple circuit that consists of an accumulator and a flag register built using the accumulator circuit, 4 separate registers to store intermediate results connected to a common bus, and an arithmetic logic unit capable of doing addition, subtraction, shift operations, and bitwise logic operations, all controlled by a series of control wires using timing from our 2-phase clock. Now suppose we want to add the contents of our 2 registers B and C and put the result in register D. First we set the write line to our register B to 1. This allows the contents of the B register to be written through the 3-state gate to the data bus. We also enable the B copy circuit, which we've added at the start of this video, to allow the contents of the bus to be copied to the accumulator. We then trigger the read clock on the accumulator to store the output of the arithmetic logic unit into the accumulator. This moves the contents of the B register into the accumulator. We now perform an add operation. We enable the 3-state gate of the C register to write its contents onto the bus. We also enable the add circuit in the arithmetic logic unit, adding the results of the accumulator and the C register. And we trigger the read clock on the accumulator, storing the results of the addition operation into the accumulator. Finally, we enable the write circuit associated with our accumulator, allowing its value to be written onto the bus. And we trigger the read clock on the D register, storing the contents of the accumulator into the D register. This is our basic computer design, controlled by a number of control wires. Now, if all these control lines could be sequenced correctly, say by the sheet music strip of a player piano, then we would have a working circuit which could perform math operations as we program it according to the music on our sheet music roll. So in this video, we finished building our arithmetic logic unit by tying in all the pieces together. We sketched the design of our basic 8-bit computer with 4 general purpose registers, an accumulator, and a flag register. And we solved 3 basic problems. We created a 3-state gate which could effectively copy the contents of a single component onto a common bus of wires, allowing us to share a single data bus across multiple components. We created a 2-phase clock timing circuit which allows us to properly time writing the contents of a register or arithmetic logic unit and read the contents once they are ready. We also created an accumulator register circuit which is capable of writing its old stored value while reading in a new value at the same time. And we showed how to use all these circuits to do a basic operation by changing the states of a collection of control wires which allow our circuits to perform a set of operations. In our next video, we'll show how to create our player piano, how to create a control circuit which can actually control the sequence of operations performed by our arithmetic logic unit and our registers. Thank you for watching.